Institute. Dr. Hall couldn't be with us today, so whenever Dr. Hall is out, I'm usually taking his spot and doing things like this. Just a little bit about the Institute. The Institute of Nuclear Security is a university entity formed right here at the Baker Center. There's a formal partnership with Oak Ridge National Laboratory, the Whitesville National Security Complex, ORAU, and of course UT. Our mission at the INS is to align the collective experience and capabilities available of our membership to grow internationally recognized resource that plays a pivotal role in solving global nuclear security challenges. And today we're having outstanding speakers, part of our Brown Bag Luncheon Series, and have the pleasure of introducing Dr. Alan Icenhour. Dr. Icenhour is currently the director of the Nuclear Security and Isotope Technology Division with Oak Ridge National Laboratory. In this role, Dr. Icenhour is responsible for research and development in areas of nuclear nonproliferation, safeguards, threat reduction, transportation security, advanced radiation detection methods, nuclear forensics, radioactive isotope production, and radiochemical science and engineering. These technologies developed by his division are used both domestically and internationally to advance scientific efforts to address nuclear security challenges. He has internationally recognized experts, some of those are in this room, within his staff who are closely involved with policy efforts to detect, prevent, and reverse proliferation of weapons of mass destruction and radiological dispersal devices. Dr. Icenhour joined ORNL in 1990 and has more than 25 years of experience with the nuclear fuel cycle, ranging from nuclear reactor operations and radiochemical research. His previous research has focused on the conversion of uranium-233 to a stable form for long-term storage studies for the effects of radiation on materials, plutonium-238 production, and development of advanced nuclear materials. He completed a 21-month special assignment in Washington, D.C. as a senior technical advisor to the Proliferation Detection Program with the Office of Nuclear Proliferation Research Development and National Nuclear Security Administration. Before joining ORNL, he served as a commissioned officer with the U.S. Navy on one of our prestigious nuclear-powered submarines. After leaving active duty, he continued his service with the Navy as an active reservist. Thank you very much. Retiring in August 2010 at the rank of captain. He received his BS degree in nuclear engineering from North Carolina State University, which we will not hold against him. His MS and PhD degrees in nuclear engineering from right here at the University of Tennessee. He's also an adjunct professor within UT's nuclear engineering department. Dr. Icenhour will be speaking on ensuring the peaceful use of nuclear technology today. Please join me in welcoming Dr. Alan Icenhour.
Thank you, Joe. It's great to be here with you, it's this afternoon now. I'm glad some people understand that it's a brown bag and that they actually brought some food because I wanted to eat with you. But I'm happy to be here at UT this afternoon. I want to talk about really a couple things. One is to give you just a little bit of history about Oak Ridge in case you don't know that, but it's right at your back door. And that really sets the stage for why is it we, Oak Ridge in general, are really involved in these issues around nuclear security. And so after that, I'll talk a bit about how we approach this nuclear security problem and give you some specific examples of that. But Oak Ridge really had its birth in the Manhattan Project. You remember that, Jim?
Sort of.
So during the Manhattan Project, there were actually 4 sites there. There was the Y12 electromagnetic separation facility. There was the X10 site that we'll talk a little bit more about in a minute. And there was the K25 gaseous diffusion plant. I said there was 4. So what was the 4th one? Anybody know? S50. What was S50?
Thermal diffusion.
S50 was thermal diffusion. It was also focused on the enrichment of uranium, and it's on, if you can see this, it's right there on this map. So during the war, there's real focus on making materials that then could be used in the war effort. And as an example, this S-50 thermal diffusion plant actually was some pre-enrichment of materials that fed into the K-25 gases diffusion plant, and then that material fed into the Y-12 electromagnetic separation plant. That was all focused on uranium enrichment. And then at this site that we call X10, and this is another picture of it, it was focused on plutonium production. This is a picture from November 1943 of the X10 site, also known as the Clinton Engineering Works because of nearby Clinton, Tennessee, and today known as the Oak Ridge National Laboratory. And November 1943, in this picture, this is a nuclear reactor. That's the graphite reactor. And it's really fascinating when you look at the history because the neutron, which is really the basis of nuclear fission that we use in nuclear reactors, was discovered in 1932. And so here in 1943, you have an operating nuclear reactor. How many reactors had we built before that? None. Okay, so there's the world's first operating nuclear reactor. And then just next door to it is the chemical processing plant. The purpose of this reactor was to irradiate uranium to produce plutonium. And when you do that, you need to use some chemical processing to separate the uranium and plutonium. So this site was focused on demonstrating the production of plutonium and the chemical processing steps. And this is really the origin. So what I showed you really in this previous picture with the enrichment type processing and of course the reactor operations chemical processing is the world's first nuclear fuel cycle. And it's these types of efforts that we worry ourselves over today in the field of nuclear security. So this place started out as X10 during the Manhattan Project, now known as the Oak Ridge National Laboratory, has evolved a bit since then. So here's a more recent picture, and actually it's hard to see, but that graphite reactor that we saw is like right in this area now. So it's still on the site. If you ever have an opportunity to go on the site, I recommend you go by and visit the graphite reactor. So today, not on October 1st, but today, we are a $1.6 billion laboratory. We have 4,000 to 4,400 employees. We also have about 3,000 research guests annually. So these are scientists and engineers that come to our facilities, work side by side with us, and they may spend a week or a month or the entire year using our facilities, collaborating on research. So that's a strong part of our staff. We've had a large amount of modernization investment, a lot of new facilities. There, laboratories, offices, test beds, new equipment stood up. And then we have a number of capabilities that we're really known for, and I'll highlight those briefly here. So the first one is science using neutrons. We do have two facilities at the laboratory. The high flux isotope reactor is the world's most intense, highest flux of neutrons. And then we have the spallation neutron source. That's a pulse source of neutrons. And both of those machines are used in really understanding the basic fundamental properties of materials. And this high flux isotope reactor, we also use it to make radioactive isotopes that have a broad range of applications. An example, right now we're working on the production of plutonium-238, which is a material that's used in radioisotope thermoelectric generators that NASA uses. So there's the Curiosity rover on Mars right now uses that as the power source. And so we're working to make the materials that are used for missions such as that. Scale computing, so large scale computing. you see the rankings come out every 6 months of the world's fastest computers. And I think at Oak Ridge, twice we've had the world's fastest computer. How about that? How does that make you feel? And we've had, I think, the third fastest, because we're in a partnership with UT and the National Science Foundation, and that one's been the third or fourth fastest computer. I think currently the Titan computer, it had been the number one, so it was like 22 petaflops. Peta is what? Where's my engineers? 10 to the 15th floating point calculations per second. So that's fairly fast. That's probably a little quicker than I can do it on my little HP. So that's a lot of computing power. Okay, and it's currently number 2 in the world. It slipped back a little bit, slowed down. We'll have to add some more capacity to that. But the interesting thing with that, it's great to have the world's fastest or second fastest, third fastest, one of these really ultra scale computers. But the most important thing is what you do with it. And so we're able to combine the programs and the people and the facilities, the capability to do the experimentation along with that computational ability, and bring all that together in the lab, and that's the real key. We are known for materials as a materials lab. I mentioned we use like the high flux isotope reactor to really understand the basic properties of materials. How do materials behave under really extreme conditions? How can I make materials that last longer? So a lot of studies along that. Of course, I mentioned our roots are in nuclear technology, and we continue to do a lot of work in that area, looking at advanced nuclear fuel cycles, new types of reactors, and things like that. But in addition to nuclear, we work across the range of sciences, biological, environmental. We have a lot of work going on looking at the effects of man on climate change, and then translating that into, well, if I've got a lot of different ways to make energy, not only nuclear, but bio-based and solar, and this all of the above strategy of making energy, how do I use it more efficiently? Because if I'm able to use something more efficiently, I need less of it, right? So we look at the energy efficiency issues. And then finally, we bring a lot of this together into our global security programs and apply our scientific know-how to help address these global security challenges. And today I'm going to really focus more on the nuclear security problem. And so we've got a lot of programs at the laboratory where we take a look at these really compelling problems that are out there that range from, there are materials at risk out there, nuclear materials that can be used by the bad guys. How do I protect those? If these materials are used in some manner, how do I understand that and recover from that? And so there's a lot of topics around that we work on. And to give some examples of the type of work we're doing, I'll talk about each of these in just a bit more detail. The first one is securing vulnerable materials, so that's protecting nuclear materials in place. If materials are in transit, whether it be coming into seaports or across borders, how do I protect, how do I identify materials that are crossing these borders? We have programs in the area of global threat reduction and material recovery, so that material that pose a national security threat, we may have to go out and remove those materials and put them in a safer configuration. We perform basic research and development. I'll give you some examples of that then has nuclear security applications. Also, this research and development has arms control verification and treaty monitoring applications. So if we enter into treaties, typically there's some type of technology component to that to help verify those treaties. We're very active in the nuclear forensic science area. Also in the area of export control and enforcement of export regulations. And there's a very heavy international component to our efforts. I'll give you some examples of that where we work with various partner countries. And this we all do in partnership through the Institute of Nuclear Security. And Joe mentioned that in the introduction. So we're very active in this institute, which is a partnership of UT, the Baker Center, Oak Ridge National Laboratory, Y12, and Oak Ridge Associated Universities. So the focus here today is nuclear security. And so what is this nuclear security challenge? And it can really simply be summed up by the fact that we understand that nuclear technology has beneficial uses, whether it be for power generation, or you or probably some of your family members have benefited from the medical applications of nuclear technology. So it has beneficial uses. But it can also be used for bad purposes if it falls into the wrong hands. So the challenge is to allow for this peaceful use of the technology while also protecting against the illicit use of the materials or technology. And that's what we try to do. So how do we know, or what do we do to achieve this thing we call security in this area? And so some examples of that are, we need to understand what the threat is that this poses. And you have to be able, in this particular case, to keep nuclear weapons or nuclear materials safe, secure, and as this says, rare. In other words, minimize them. We have to preferably eliminate, but at least reduce or minimize the potential use, the risk of malicious use or theft. We need to reduce the potential threats, and if there is a threat that we identify, we need to be able to trace it back to its source. If the material is used for some illicit purpose, such as, say, detonation of either a nuclear device or a radiological dispersion device, we want to be able to minimize the damage caused by that and be able to recover effectively from that. And in all cases, we need to be able to ensure that we can sustain this strategy. And the key to that is having knowledgeable people that are working on these issues. So in this area, we face a wide spectrum of challenges. We may have individual actors who are attempting to obtain and sell material. Certainly there's the ever-present terrorist threat. We have nation states that every time you open the news, well, you guys don't look at newspapers, do you? I still look at the newspaper. You probably don't. Okay. Every time you look at the news, turn on the news, you know, you'll see something about these, and certainly the one at the top there is very heavily in the news as we continue to have dialogue about that. And then there's the threat of the transnational networks, and the example there, of course, is the AQCON proliferation network. So you can see there's a range of challenges that you have to be able to address. So to do that, it takes not only policy efforts and diplomacy, but also usually technology involved in some ways. And so I'm going to give you some examples. I won't read this list. I'm going to give you some examples about each of these areas to show you how technology is deployed. What role does it play? And so the first area, this international safeguards. And in that area, we work with partner countries through the development, testing, evaluation of technologies that can be used to strengthen their safeguards. We provide a lot of training. We serve on inspection teams, we provide technical support, we perform proliferation resistance studies. So there's a lot of analysis and studies, provision of technology to partner countries. Now, supporting that is our Safeguards Laboratory, and some of you may have benefited from the use of this laboratory. In this facility, we have a variety of nuclear materials, nuclear sources, radiation detection, radiation detectors. We can configure these materials in a lot of, we can place these materials in a lot of different configurations, and then we can use those to demonstrate Safeguards concepts, the use of detectors, and we do that with university classes. We typically have about 6 or 7 different universities, including the University of Florida. That come through every year and make use of this, but we also have professionals that come through and make use of this facility, and we work with industry to test out their equipment. So this is a real resource that's used by multiple organizations. Another area is more broadly in this non-proliferation engagement, training, and outreach. And I gave you a couple examples already of how we're involved in this through kind of our Safeguards programs as well as our Safeguards Laboratory. But we do a lot of international engagement, whether it be through the International Atomic Energy Agency or directly with partner countries on Safeguards topics. And of course, a lot of that's through training and workshops, but we also engage a lot through professional societies such as the American Nuclear Society and the Institute for Nuclear Materials Management. And I encourage you, if you're earlier in your career and you're not already involved in a professional society, is to get involved, because that's a great way to meet people who are working in an area that you have the same interest in. And if you have interest in this area, certainly through the Institute for Nuclear Materials Management and the American Nuclear Society, 2 great organizations to connect with professionals in that area. Now, changing directions a little bit here to talk about international export control. And are any of you familiar with export control laws? Are any of you experts in export control? Okay. Yeah, it's export control law. Well, there's a reason I'm not a lawyer. Okay. Nuclear engineering is a lot easier than export control laws and regulations. Very complicated. It's not only U.S., but other countries have their own laws and regulations too, and navigating that minefield of law. So it's all focused on this thing that, you know, again, nuclear technology, nuclear materials have peaceful uses, but if they fall into the wrong hands, it's not good. Okay, so how do we prevent that? So one of the mechanisms through export control laws, export control regulations. And so we have people on staff at the lab that have a lot of expertise about the nuclear fuel cycle, the types of technologies that are used. So they developed an expertise in these export control regulations. And so we work both domestically and internationally with border control agencies and other officials to educate them on the export control laws, whether it be U.S. or specific to their country. And so if you're a border control agent and you're seeing materials come across the border, what is it about that that makes me say, well, that looks suspicious? Max, that does look pretty suspicious. What have you got there? Have you taken that into a football game? I hope not. What is it about that I should be suspicious about? And so we equip these people to at least the point where they can raise the flag and say, you know, that looks a bit suspicious. Let's stop and look at this in a little bit more detail. And we're also involved on the other end of the spectrum of interdiction, because we're always out there looking for the bad guy or gal that's trying to use this material for wrong purposes. So we're involved with that. We consult with law enforcement agencies quite a bit on helping in the interdiction of these materials or equipment. So if we do have nuclear materials, or a country has nuclear materials, they need to be able to protect it appropriately. And so some of our programs are focused on how do you secure nuclear materials in place where they exist. So we can call that the first line defense of protecting materials. And so example, if you look at the upper picture there, that's a facility outside of Moscow. When the Soviet Union collapsed, that infrastructure that protected their nuclear materials collapsed along with it. And so you had a lot of facilities that were essentially abandoned, but they still had a lot of nuclear material inside them. And so we worked very closely in Russia to upgrade the protective posture of their facilities. That includes a lot of fences and cameras and other detection technology to help protect those materials, but it also includes doing things like establishing inventory control type programs, because if you don't know what you have, you don't know what you have, right? And so you need to have programs in place to track these materials and to keep up with them. Well, obviously, if you have a first line of defense, there must be a second line of defense, right? And so the second line of defense, if there are materials that are in transit, if they're going across borders, if these nuclear materials are coming into seaports, how do you identify them? And so there's the program, it's called the second line of defense, and it's focused on border security. And it involves primarily installing things such as these radiation portal monitors. So if material is giving off, a radioactive signature, you could detect it and identify that it's there. And so we work on the installation of these portal monitors all over the world. We also test them. We have test beds at our laboratory, so we have an indoor and an outdoor test bed. And then these portal monitors that are installed over the world generate a lot of data, okay? And so we have people with the expertise that can take a look and weed through all that data and really understand how they're operating and understand what you're getting out of it. So this is not the third line of defense. Maybe I should label it that way. But another action you could take is, well, we protect the materials in place. We've looked for materials in transit, but if there are nuclear materials that are in a situation that's not very safe and they really shouldn't be there, sometimes you just have to go remove them and put them in a safe situation. And so examples of programs, there's this Russian research reactor fuel return program. And so there were a number of research reactors that Russia sponsored around the world, and they were fueled with highly enriched uranium. Highly enriched uranium is a material that could be used for illicit purposes. So that's a concern if you've got it, say, on a campus somewhere that's not very protected. Okay, so there's programs to remove both fresh and fuel that's been irradiated or spent fuel, and then to convert reactors from the use of high enriched uranium to low enriched uranium. We're involved on those. We also work on programs such as in Kazakhstan, there was this BN-350 reactor. There was 300 metric tons of material there that had the equivalent of about 775 nuclear weapons worth of material in it. And so through that program, we worked to place that material into safe storage into casks that could be transported and then moved it to another location in the country where it's better protected. And then a final example of a program that we work on is this mobile uranium facility. This is a program that we work on in partnership with the Y-12 Nuclear Security Complex. And in this, we've developed these mobile facilities. So these are standard military cargo containers that the sides fold out on. And inside them, we've equipped them with laboratory equipment, such as glove boxes and analytical equipment, repackaging equipment. And this type of facility then can be deployed anywhere in the world with a little help from our friends in the Department of Defense to deal with materials that need to be removed. And of course, one element of all this work is transportation, because if you're moving materials around, you need to be able to do it securely. And so we've worked on programs in the transportation security arena to do things, and some of the examples here are making secure rail cars. So security features on rail cars, these overpacks that go inside of rail cars, designing, procuring those, the other associated transportation vehicles you may need, participating in technology demonstrations, and then the associated communications, and working on the technology to tie all that together to be able to communicate and to track the materials in transit. So we work on those types of things as well. So now I've changed direction a bit and talk about radiation detection. This is where I get more into some of the basic science of what we do, although I'm not going to go in real detail here, just to give you an overview of some examples, again, of how technology is used. And our work using radiation detection fits in the nuclear security arena, fits kind of in three basic areas. One's in this kind of traditional safeguards area where you're trying to, say, for example, count how many spent fuel elements that you have and keep up with that. It's an inventory type approach. There's also the arms control and treaty verification type applications, where if you're in a treaty with a country and they're reducing the number of warheads they have, how do you count those, and compare notes and say, yeah, we agree with you, and we're both abiding by the treaty. And then the final area is this what's characterized, you may hear it, loose nukes. So in this application is where you're looking out in the environment for these materials that are out there that aren't supposed to be out there. So some examples of this. This is kind of in this treaty verification mode. This blend down monitoring system was developed. Jim, you were heavily involved in this, were you not? Maybe I should let you give this talk.
You're doing great.
Okay. Blend down monitoring system. There was an agreement between the U.S. and Russia in 1993, the HEU Transparency Agreement, to blend down 500 metric tons of highly enriched uranium that was formerly in Soviet warheads. Okay, so this material was taken from highly enriched uranium to low enriched uranium, and then sold through the United States Enrichment Corporation for fabrication into fuel in U.S. reactors. Think about that for a minute. Okay, so furthermore, about 20% of the electricity in the U.S. is generated by nuclear power. About half of the fuel for the U.S. reactors comes from this program. So that means about 10% of the electricity in the U.S. is generated by materials that were formerly in Soviet warheads aimed at the U.S. Okay, that's kind of ironic. Okay, well, that's a great story unto itself. So what does technology have to do with that? Well, this was an agreement to blend down 500 metric tons. So, and the Russians are doing this. So how do we know they're doing what they say they're doing? You know, you can stand up a plant and say, there, I'm doing it. But how do you know they're doing it? So technology was developed, partnership with Oak Ridge National Laboratory and Los Alamos National Laboratory, developed this blend down monitoring system to look at a feed stream of highly enriched uranium, a blending stream of low enriched uranium, and then a product stream. And by tracking the material balance in each of those streams, you can assure yourself that indeed your partner is doing what they say they're doing. It's been a very successful program. This is a little bit dated here, so 475 metric tons of the 500 blended down by this past June. The program's actually going to wrap up, well, in November, so just in a little over a month, it will wrap up.
In what form is that stream?
That's UF6.
Okay.
So another area we work on is coded aperture imaging. And so this is imaging, looking for and identifying radioactive sources, whether it be inside of facilities, in the environment, along the roadway, or maybe even on the water. So examples of that, and we have a couple different approaches. One is gamma ray imaging. And so in this, we're taking advantage of this technology, which is in the white trailer here. So with this, so you take on faith some of this. But with the white trailer, I can look out into the environment and I can identify there's a radioactive source over there. Okay? And given the characteristics of that source, I can even identify what kind of source it is. So combining that with, say, on this long boom, I have a camera looking down on the traffic. I can track individual automobiles or trucks, and I can attribute that radiation signature to a particular vehicle that's going by. And so you're able to track individual vehicles and identify the sources in them. So that, you could imagine, would be very useful if you had something such as at a big toll or a border crossing. Now this type of concept has actually been extended to, here you can see it's on a pier looking out at boats going by. And then it's being extended further up here in this very fancy picture of looking ship to ship. And that's where you have to correct for, I'm an old Navy guy, so I understand that, you know, these boats, they can rock around quite a bit. So you have to correct for that motion in that. So that type of work's going on. Another area of effort is in neutron imaging. And with that, we develop detectors and detector systems that can be used to look at neutrons. And then there are applications for that, such as being able to look at materials and identify, say, where the uranium is. Can anybody tell me where the uranium is in this picture? That's pretty handy, isn't it? It just jumps out at you. Up here is an interesting experiment that was done where it looks at in the middle. This is just a plate that has 5, and you may be able to see 5 points on that plate up there. Those are californium-252 sources. And the neat thing about californium-252 is it's throwing off neutrons. So it's a neutron source. Okay. So using this system here, you could image this plate. This was really a high-tech experiment because the californium sources were placed on there with duct tape. Nuclear-grade duct tape. But with that, it produced this image. Okay? And you see this was imaging with sufficient resolution to count warheads. Because you can imagine you're looking down on the nose cone of a missile, you know, but there's a cone there. You can't see inside it. Okay? But you, my friend, have told me there are 5 warheads in there. not 6, not 4 or 5. You told me that. With this kind of technology, I don't have to remove the cone because you don't want me to see inside the cone, right? And I can count. Yeah, it looks like you're right. There are 5. Another application, and this is a mock-up, is there's a concern with regard to spent nuclear fuel has plutonium in it. So there's a concern about the diversion of spent nuclear fuel, and nuclear fuel typically consists of fuel pans that are arranged in a bundle. And there's a concern that maybe someone could just remove a few pans here and there over time and steal those and then recover the plutonium, and you wouldn't even know it. So using this type of technology, again, you can look down there and you can see where there's a missing pan. So just a couple of examples of applications. So the development of new materials to assist in the detection of radioactivity, and in particular for nuclear security, plutonium or uranium or some other type of radioactive sources. So we do a lot of work in the development of nuclear materials. So we develop acetylator materials. We do a lot of work on helium-3 replacement. Helium-3 is a material that's used for the detection of neutrons. And it became very popular post 9/11 when Jim and other people started putting these portal monitors all over the place, and they started consuming all the helium-3 inventory. And so with that, we need alternatives to that, you know, in turn, but you want things that can give the same kind of performance. So we do a lot of work on that, developing new materials for helium-3 replacement. So the radiation detection, one of the things it does for you is help you in nuclear forensics efforts, and I'm going to talk a bit about nuclear forensics here. When you have a forensics question, have any of you watched CSI? The best thing to do is to go to CSI and use that approach, right? You got 1 hour, and during that hour, which you have to cut it back to about, 40 minutes, because there's at least 20 minutes commercials, you know, they have the best parts at the beginning of the show, right? Because you always have the crime, and it's always something crazy. But then they go out and they do the crime scene investigation, they get their samples, and they go back to the lab and they put it inside of whatever device they have, and then they got a great computer screen that prints out, or it shows up, you know, exactly what the material is, who bought it, when they bought it, puts a picture of the person up there and everything, right? That's the way it happens in the real world, right? It's just as easy as that. Well, not really. So in the forensics game, you have 3 basic questions. And let's think about the Boston bombing. So when the Boston Marathon bombing happened this year, they had 3 basic questions. What is it? Where did it come from? And who did it, right? And that's really the kind of simple questions you have when you're in the forensics game. And of course, there are a lot of underlying questions to each of those that you have to be able to answer. But in the nuclear forensics area, when you obtain material, whether it be a gas sample, water sample, a swipe sample like they do in CSI, you have to be able to receive and protect that material and maintain the chain of custody of it. And then you have to be able to analyze it. And in this case, we're talking about materials that have some radioactive characteristic with them potentially. So you have to have appropriate facilities to do that. And you have to have a whole suite of technology. I mentioned radiation detection is very helpful, but also mass spectrometry, other chemical analyses are very helpful in this. And so I get samples and I analyze them, and then the hard part starts of, well, what does it mean? Because I get a lot of data, you know, lots of numbers or you know, spectra. What does it mean? How do I interpret that? that goes back to my very first slides, where you go back to what's this basis of understanding and expertise around the nuclear fuel cycle. And so you really have to understand the characteristics of facilities, the characteristics of processes, in order to be able to interpret all this data. Okay? And so that's why, we've got a real, pardon the pun, critical mass of expertise in Oak Ridge around the nuclear fuel cycle. So we're able to look at a lot of this data and understand what's happening, what's the processes, and how can I better obtain data from this information. So I gave you an example of quite a number of different technologies that are being used to protect nuclear materials to help ensure nuclear security. But technology is not the only answer, and it has its limitations. And some examples of that are, a very basic question: how do you know what you're looking for in the first place? Am I looking for materials being smuggled? Am I looking for nuclear weapons? What am I looking for? Really, you gotta have a good understanding of what you're looking for in order to know how to look, right? And so, an example, are declarations complete? If you and I enter into an agreement, you're going to reduce the number of nuclear weapons you have, and I'll do the same. How do I know that when you hand me that piece of paper that says, I've got 10, and I've got 15, okay? How do I know that that's a complete declaration? That's a real challenge, This thing, material unaccounted for. If any of you worked in processing materials, there are always losses of materials, right? And in nuclear jargon, we call that material unaccounted for, MUF. Okay. Well, you always have losses or hold up in processes. How much is too much? And can that be actually used to shield, okay, I'm putting a little off to the side here, and I just write that off as material unaccounted for. So that's a real challenge. Typically, when you're in this arena, there's not one smoking gun that tells you what's going on. You have to look at multiple sources of information. And if I'm working with you, say we're in an agreement, an arms control agreement or arms reduction agreement, have to balance how much information that I gain with how intrusive you let me be. Okay? Because you may not want me to see everything about all your programs. So that's a real balance that you have to walk. The real challenge is that people are involved in the process. And just back up and think about things that you've seen in the news fairly recently. We've had the trial for the Fort Hood shooter and insider job, right? We just last week had the shooting at the Washington Navy Yard, and maybe there's certainly some mental imbalance there, but also there was insider job, insider access. So there's this whole question of human reliability that you have to deal with in all these areas. How do I trust you? And importantly, how do you trust me? And then how do we verify that we can trust each other? Okay, so that's a real challenge. And then the final I'll talk about here is sustainability. Is that, it's great to put all this cool technology in place, cameras, detectors, all these systems, even processes. But how do you sustain it? You have to have people with the expertise and also the passion to do it involved in the process, and that involves continued outreach and education and understanding of these issues, because you have to continually feed new people into this to sustain this. Because this is not a problem that is just solved and done. It's an ongoing challenge. So, to conclude, the Nuclear Nonproliferation Treaty has three basic pillars. One pillar is that states that do not have weapons, non-nuclear weapon states, will not obtain them. The second pillar is that weapon states, those that have nuclear weapons, will reduce and ultimately eliminate those weapons. And then the third pillar is what we call this peaceful uses pillar, that recognizes that nuclear materials have beneficial uses, again, for things such as energy production or for medical purposes or use in other industrial applications. So it has peaceful uses, but those materials and the technologies can be diverted to illicit processes. And so it's those concerns then that lead us to this whole nuclear security effort. And technology then plays an important role in helping to ensure nuclear security. Thank you.
We have plenty of time for questions for
I shouldn't have left as much time. Jim.
Dr. Icenhour, what do you see as the opportunities for the University of Tennessee and its professors and its students to participate in this mission for non-proliferation?
There's a couple areas. One's the obvious, since I'm a more technology geek, is to work on the development of new technologies. You know, whether it be radiation detection or other types of technologies, or, you know, in the forensics area, radiochemical type technologies. The other area is on the policy side, and certainly through the Baker Center here, is working on helping to obviously educate students about these issues, but also more broadly, and they're probably more capable of connecting with our policymakers on helping to inform them about these issues. And the part about that is bringing together the policy world and the technology side of the house, and getting both sides talking together. And the university plays a good, is a good forum to do that in.
Now, this is more anecdotal, it's kind of off the wall here, but since you're reading integrity newspaper, and since you work in this industry for a long time with acquiring new materials, with what's happening with Iran and their new leader, what's your opinion where that's going to go, and how can ORNL play in that if they truly want to open up their country and bring folks in to look at what's going on there?
Well, I don't know that I'll state an opinion on that, but I think it's very early. It's very promising to see their discussion about this now. Okay, but of course it's very early, as in this week that it just started, that there's some indication. As those discussions, if they proceed, which I'm hopeful that they will, and that there are some agreements entered to, again, there's a role for technology, because ultimately this would lead to some type of agreement, maybe not a treaty, but an agreement. The IAEA would be heavily involved, I would assume, but there would be technology that would be applied to verify that the agreement's upheld. Yeah.
I guess on the helium-3 thing,
Yeah.
so I think I understand that we were getting helium-3 from like our, I guess, thermonuclear bombs, I guess, is that right? I think it was decaying.
Well, there was helium-3 was a side product of kind of the weapons production industry.
Is there a way
Yeah.
to, like, I guess, simulate that process if it's like a very important expensive material? Is there a way to like go through some of those processes without creating?
Well, there are a lot of alternatives that are being looked at to see, and because you have to be able to, one, understand how good is good enough if I'm looking for neutrons, how good does my detection capability need to be, and also, if it's something that I'm going to deploy, ultimately it needs to be economical. Okay, and certainly helium-3 was a material, I guess, of convenience because there was for a long time a good steady supply of it. Okay, but ultimately you need good economical solutions, and that's what we'll carry today in that area, I believe.
You talked about all these programs Oak Ridge has available to it in the umbrella of nuclear security. Where are Oak Ridge's strong points in relation to the rest of the DOE laboratory complex? I mean, like, what are our shining stars? Where are we going to move forward?
Well, certainly this whole area of radiation detection, we're world leaders, and we've got world experts in that area. We also, in the development of safeguards technologies, and in sections of, or in portions of nuclear forensics, some of the technologies that we develop there, I think, we're world leaders in our technology applications there. So we've got, a lot of efforts that I would consider world leading.
I would add, Alan, that
Yeah.
we would, that we have extreme expertise in operational capabilities. And, folks like coming from Y12 who've had their hands-on materials, unlike the other laboratories. So we have a significant
that's an
amount of
excellent
folks.
point.
And Jim, you want to answer that?
Basically, the front end of the nuclear fuel cycle.
Right.
I mean, that's where we got our start in the Manhattan Project, was the front end of the fuel cycle, making the material, like Alan said. And we know those processes. We have the subject matter experts, both at Y12 and ORNL,
Yeah.
who have that expertise.
So when you think about uranium, people in the business think about Oak Ridge. Yeah.
You have a follow-up?
No.
Oh, okay.
I just wanted you guys to highlight the bigger portions of that.
Jim, you
What would you say are the two, if you had to pick two cutting edges for the technology associated with nonproliferation, what would they be? You went through several in your slides. I was just wondering if you could pick a couple that you think provide a lot of opportunity for research and development and scientific study.
Well, I'll come back again to the radiation detection area, because there's the nice thing about radiation detection, it's not just the nuclear security game. We've got physicists here, I know, and so there's a lot of basic science needs in that, and it's been interesting, some of the detection technology, some of you see starts out with kind of the basic science application. It transitions over to maybe a nuclear security type application, matures some more, and then it's actually gone back after it's matured, and it kind of just ratchets up. That's been very interesting to see that happen. And then again, in the nuclear forensics area, the development of new techniques and capabilities there, I think there's a lot of opportunity there as well. And a lot of that has underpinnings in the basic science, whether it be in chemistry, nuclear chemistry, radiation detection.
And so NNSA has an office of research and development. You were there for a couple of years. You helped establish certain versions of the research and development agenda.
Yes.
So, and part of that each year is given out to universities for competition for research and development to support nonproliferation, right?
Well, it was.
Oh, it was. So the university didn't
well,
step up? What happened?
No, they did, but that's changing now because they established one consortium, funded at $5 million per year, and they've had a competition recently for 2 more. And so they're going to funnel their university efforts through these consortium. They'll have 3. So one of the consortiums focused more on the traditional radiation detection type technologies. One's on development technology for more, I guess I'd call it forensics based. And then another one's kind of broad. It's enabling capabilities, so they're basic science capabilities.
And UT's involved.
Yeah.
Good.
Through the institute.
So what would you see then as an opportunity for policy breakthrough, cutting edge? I mean, we talk a lot about technology, but what about policy?
Boy, now that's a good question. I'm way out of my water on that one. You know, where's the breakthroughs in terms? One breakthrough, both for technology and policy, is for the 2 communities to continue to talk and interact a lot together, and the policymakers drawing upon the technical experts to understand what is possible. But that goes true when you turn around the other way too, because the technology expert also needs to understand what's politically possible, which is often one of the bigger challenges that you face. But there's that communication between the communities, and I know that's happening here, you know, through the Baker Center, the Global Security Program.
We're doing it
That's
now.
healthy. Yeah, and we're doing it now.
Right.
Yeah.
Just wondering, does ORNL, you know, they work on the technology for detection, but do they have any role in, I guess, updating threat assessments and doing an analysis on countries potentially declared threats, reviewing the information?
We work with a lot of agencies that draw upon our expertise. Jim, do you want to answer that?
Well, no, I'm going to change the subject. That's near and dear, but anyway, why don't you talk a little bit more about, one of the questions we talked a little bit about is what could happen in the real world with Iran, North Korea, you know, coming down the road, and how can Oak Ridge National Lab and Y-12 play a role in that? Why don't you talk a little bit about some of the past efforts that we've done?
Well, don't you, since you did some of the past efforts.
Well, I mean, well, we've been involved. Well, Alan kind of touched on it briefly and introduced them. I think the first effort we did in Oak Ridge as a team, here again between Oak Ridge National Lab and Y-12, was in Kazakhstan. We learned that there was something on the order of about 600 kilograms of weapons-grade uranium that was stored in a shed in Kazakhstan with a rusty padlock. I mean, literally, that was the only protection for this material. 600 kilograms is enough to make 24 nuclear weapons. And we put together a team, worked with the Department of Defense, deployed the team to Kazakhstan, repackaged the material, brought it back to Oak Ridge, took it to Y-12, and where it was eventually dispositioned. And you were involved in some of that, weren't
Yeah,
you,
I
Joe?
saw that material go from high enriched uranium in a solution lead to low enriched uranium and converted to UNH crystals and shipped off to a commercial fabricator to make U308 to make pellets to go into commercial reactors. So I saw
So
that.
we had people on the ground in these countries pulling this material out, securing it, and getting it out of harm's way, basically. More recently, in 2004, Muammar Gaddafi gave up his nuclear program in Libya after we caught him red-handed, basically, but that's a whole other story I can't get into. We helped evacuate 550 metric tons of nuclear materials and equipment and raw materials, everything, from Libya, brought it by combination of C-17 aircraft and cargo ship to Oak Ridge, Tennessee. We had boots on the ground in country, gathering the material, packaging it, and getting it out of there. We then went after the key guy that sold all that stuff to Libya, that's A.Q. Khan, and we worked with the prosecuting authorities around the world to put his network out of business. So we play a key role both at Lycwell and ORNL in world events.
Where do we stand on that Soviet material being downblended and going to the nuclear power industry in this country? Have we utilized most of that?
Yes.
In a sense, we have now we didn't need to generate our own enrichment capability because we had that as a source. Has that been used
Well,
up
it's
now?
about half of the enrichment capabilities was provided by that material.
Has that been used now?
It's
Yes,
has
that
been
program's
used over the
ending in
last 20
November.
years.
Yeah.
And Lee, off-spec material. During the midst of acquiring material from other countries, the U.S. had a lot of off-spec HEU that went to downblending that supplied commercial reactor. That went to downblending to supply.
But like Alan said, that program has grown to a close. The last small quantities of material is working its way through the system now, working its way into fuel elements.
Because we don't have much enrichment capability in the country.
Well, there's quite a bit. Actually, not domestically owned, but there's the Eunice, New Mexico. There's the plant there that's operating, and they've actually, I think, fairly recently slowed down their expansion efforts.
Is that a centrifuge plant?
Yes, it's Urenco.
Okay.
But the problem is we got this little thing called shale gas out there, and that's depressed the price of uranium. We've also had, of course, the events in Fukushima, and so the demand has went down quite a bit. So that's put pressure on the production side.
Chris had one back here, Chris.
Any thoughts on quantifying? I mean, how much better are we, say, 10 years ago? I mean, we were spending a lot of money on it, and it's pretty widespread. Are we spending it on your thoughts on, are we spending it on the right things? It should be more of this or that?
Well, I think, of course, this cooperative threat reduction program, the non-Lugar program, actually Senator Lugar was here. I don't know if any of you saw him recently, very good talk, has come to an end. I think we're in significantly better shape than where we started, because we were in a very precarious position when the Soviet Union collapsed and these materials effectively left unprotected. And so the types of programs that we put in place, and then we also have to face the reality. There are a lot of countries that are very aggressively pursuing nuclear power. And so as they do that and they try to obtain those technologies, we need to have the programs and partnerships in place to work with those countries to educate them about the kind of things, of course, that we as a country learned about since, the end of World War II. Somebody's just getting in the game now. How do they ramp up that infrastructure and get all that it's a culture. It's a security culture. How do you get that in place? And so I think the types of programs that we do have significantly improved that, and they'll continue to pay off. And certainly universities play a key role in that as well.
Do you believe our efforts are changing from the concern being the Soviet versus now the smaller?
Yeah, there's no doubt they're shifting, because there's been a tremendous amount of effort in Russia in particular. That's winding down, but there's still other threats out there. There's that whole spectrum of threats that you have to protect against, and so there are shifts in that.
I mean, I have lots of questions. Are we almost getting to the point where we're too dependent upon technology and not enough, I'll use the word spies overseas?
We want to write this down, go slow.
There's covert intelligence from overseas, which
The thing I said, there's no smoking gun. It takes many many different methods.
That's what I'm saying.
To get that, and are we too dependent?
heading-
It's hard to quantify
I
that.
mean, are we heading down a road though where we think that technology is the end all, where a lot of people will think technology is the solution?
Some people think it's not, though. Technology is not the end-all solution.
And Alan,
Yeah.
correct me if I'm wrong,
Yeah.
I know just a little bit about this, so forgive me if I say something
Yeah.
wrong, but DHS certainly has their DNDO office, which is concerned about things, and they're doing some things that are not technology related, but more architecture related for the detection of nuclear materials, and having an infrastructure there of capitalizing on all data, whether it's intelligence data, data like, what ships are coming in, what things are being transported in order to detect if something's going to come into the U.S. And I hope I gave that fair justice with the work that you guys are doing.
Yeah, I think that's pretty.
Tom is just trying to see when he retires as a professor of physics, is there a job for him as a spy?
There probably is.
The other serious question I have is these portal detectors, what's the smallest amount of material you can actually, because you don't have to set off a weapon. You mentioned is the radiological
I
dispersion.
can't speak to that.
Not in this environment.
Yeah.
Next question. Any other questions from everybody? Anybody? All right, let's give Alan another round of applause.